Tonight is the second in our annual new series, the Lee and Niall Albright Annual Symposium. Dr. and Mrs. Albright have established these symposia as a way for us to spotlight the museum's new Hall of Human Life exhibit and notable scientists whose research focuses on human biology and health. We are honored to have the opportunity to present this series and are very pleased that Dr. Albright will introduce our special guest. So please join me in extending heartfelt thanks to Lee and Niall Albright and in welcoming Dr. Albright to the podium.
It's a great pleasure to see all of you here tonight and recognizing some that were here at the first inauguration of this symposium last year when we had an extraordinary presentation by Tim Spector, who is the holder of the world's largest collection of identical human twins. And he's the one that during the symposium was signing books at the end of it about his recent book that was published that same month, Identically Different. And he presented last time something that I was never aware of all the way through medical school and residency and training, that we can affect our genes. And he has shown that with these identical twin studies of how these identical twins do vary and become different because their genes do change from the experiences each one goes through during life. Tonight we're really favored and pleased to have a world-class gentleman who's going to bring you through the intrigue and the puzzles and some of the solutions to the most difficult, least understood organ in the body, the brain. And it applies to all of us because the buzzword for all of us, particularly as we get older, is what is memory, how does it act, and what can we do to improve it? And you're going to hear tonight about terms you may not have heard before, about the consolidation of processes in the brain, then the integration of these processes, our speaker is going to tell us about and explain, and how this affects from our nighttime brain activities to affect the critical memory that we possess during the rest of our day. So it's with great pleasure I'd like to introduce Robert Stickgold, who brings a world-class perspective, has talked to many people in many countries as well as this country, and most importantly, we both went to the same house at Harvard College when we were growing up in the 60s. Robert, you're on.
Thank you. Well, thank you, Niall, and thanks to the museum for inviting me here. The important part of that last sentence of Niall's was not the bit about Harvard, but about growing up in the 60s, but that's a different talk. Oh, I am, yes, we have done magic. Are we? That's okay, we'll get it going again. Sure, why don't we do this? Is that? There we are. There's my title for tonight. Sleep, Memory, and Dreams, How the Brain Keeps Working All Night. So my research for the last 15, 20 years now has been looking at how the brain processes information while we sleep. And although that's going to be a big chunk of what I talk about, I usually have this throwaway at the start of my talks about how that's not all that's happening while you sleep. And for tonight, I think I want to spend a little more time just giving you a sense of all the things that are going on, all the things that are happening in your body, in your brain, while you sleep, while you seem to be just turned off and doing nothing. So sleep doesn't just cure sleepiness. It was in 1998 that Alan Hobson at Harvard complained that the only known function of sleeping was to cure sleepiness, which is a little bit like saying the only known function of eating is to make you not feel hungry. And of course, feeding, eating has an important biological function. But back in 2000, we had no idea actually of any biological functions for sleep, which was really striking. And it's been a very exciting 15 years because we've learned all sorts of stuff. So sleep is critical for hormonal and immune function. I'm trying to get used to where I want to stand for this. It's kind of strange. Maybe I'll stand here for a while. So if you take a group of college students and you restrict their sleep to 4 hours a night for 5 days, their insulin regulation goes totally haywire. And the subjects start to look pre-diabetic. So what does that mean? Well, if you take someone and give them an IV glucose tolerance test, you inject insulin and you watch how the insulin works in their body, what you find is, well, if you have a healthy control, when you give an insulin injection, the body will clear out about, 2.5% of the glucose from the blood every minute. That's how we can keep our, you can take that if you want. That's okay. I used to have a slide that says you can talk on your phone if I'm discussing data, but not if I'm discussing ideas. So a healthy control subjects, just normal, healthy, young subjects, clear about 2.5% of the glucose out of their body every minute if they drink a Pepsi or something, taking a big chunk of sugar. In contrast, if you have an elderly person who's edging towards type 2 diabetes, you'll see a clearance rate of maybe 1.4% per minute. But when you take these otherwise healthy college students and put them on 4 hours of sleep a night, 5 nights, and do the same test, it does not look good. So these kids now look pre-diabetic. Their glucose regulation, their insulin regulation is totally off, and their body is not sequestering and processing glucose the way it should. And this has led to the suggestion that this blunted insulin response might be part of the reason that we have this epidemic of obesity in the country, that it actually might be an epidemic of inadequate sleep, because inadequate sleep will tend to cause a type 2 diabetes type syndrome that will lead to weight gain. So that's hormonal function. What about immune function? Well, you can take some college students. We take college students because they're cheap. They're dime a dozen. In fact, their parents pay. I'm not going to go there. So this is a study where they gave college students a vaccination, a standard vaccination for type A hepatitis, and they took half the students and then sleep deprived them the following night. The night after they get the injection of the vaccine, no sleep. In fact, no sleep until bedtime the next night, no cheating the next day. So what happens when you get a vaccination or when you get a cold or when you run into even more dastardly viruses or bacteria is your body mounts a series of responses. There's an immediate response, but you don't get the full response for about 4 weeks. So if you look at the amount of antibody to the hepatitis A that's being produced in these two groups of subjects, out to about 2 weeks, they seem to be lying right on top of each other. But over the next 2 weeks, they diverge. And so at 4 weeks, when you've sort of got that full immune response produced, you're 49% down. 1 night of sleep deprivation is all it takes. And so you think about kids in school, grade school, college, I'm sorry, you think about adults now too, who catch a cold, and then they can't be bothered that night, and they work all night, and their ability to start to mount those immune reactions is compromised. We need sleep for our immune system and for our hormonal systems to function properly. Sleep is critical for psychiatric health. There's been known for decades, if not forever, that every major psychiatric disorder has as one of its characteristics a disruption of sleep. So if you have depression, you don't sleep so well. If you have manic depressive, bipolar disorder, you don't sleep so well. If you have schizophrenia, you don't sleep so well. And the sort of sloppy assumption has always been, well, the reason they don't sleep well is, you're depressed, you don't sleep well. So the causal arrow has always gone from the psychiatric disorder to the sleep. But people have started looking at it more closely, and it's a lot more complicated than that. If you look in just the general population, this was a wonderful telephone survey of 20,000 Brits and Europeans. And they asked them questions about, did they have sleep apnea? Did they have depression? Other things too. Sleep apnea is a breathing disorder. It's a sleep disorder where while you're sleeping, the airwaves collapse. In the airways collapse. And so you go, right? Anybody have a spouse who snores? Huh? Anybody kick them out of the room yet? No? I got to stop doing that. A lot of the referrals to the sleep labs are men who come in and say, you have to do something for me. My wife says she's throwing me out of the bedroom. So this is just a mechanical problem where the airwaves collapse because of weight, usually from excessive weight in the throat. That was a mistake. So if you look in this general population survey of 20,000 people, and you find the people who have apnea, they're 4 times more likely to be depressed. That's a huge increase, 4 times more likely. And you might think, well, there aren't that many people with apnea, so it's not that big a thing. But actually, if you look amongst depressed people, they're 5 times more likely to have apnea too. So there's a huge overlap in these two populations. And if you're not sure what's going on here, well, here's a study where they found people who both had apnea and depression, and they broke them down into those who had levels, I'm getting my pointer to come on, there we go. Those who had depression ratings above 50, which is the level that's defined as clinically significant depression, and the others who didn't reach the level of 50. And the ones with 50 and higher had more apnea. This is the number of times, by the way, each hour that they stop breathing. And they actually wake up for a couple of seconds. So these guys, and it's not uncommon in our culture at all, once a minute, they'll start to snore, they'll gasp, they'll stop breathing, they'll wake up because the brain wakes them up, and then they start breathing again, they fall right back to sleep. They don't remember any of it. Can I say this? They feel like shit the next day. They're just exhausted, even though they think they've slept 8-9 hours. So in this study, Millman took those with the higher ratings, and he got those who were willing to come back again, and then he treated them for their apnea with what's called CPAP, continuous positive airway pressure. You just put a little mask over their faces, and it blows a little air in, and it's like keeping a balloon mouth open. It just expands the airways enough to stop that collapse. And when they treat the apnea, the depression drops below clinical levels. With kids, you see the same thing except with ADHD. If kids have ADHD and apnea, and you treat the apnea, you get a larger reduction in their ADHD symptoms than if you put them on Ritalin. Okay? So it's very clear that this disruption of sleep is a major contributor to at least the intensity of these psychiatric disorders, and sometimes makes the difference between whether it's considered clinically significant or not. One of the things that they just came out with this year that sleep does, that I love, is that sleep scrubs your brain. I didn't put it that way. It turns out that when you go to sleep, all your brain cells kind of shrink a little bit. And the spaces between the cells enlarge. And with those spaces opening up, it becomes easier for cerebral spinal fluid to pump through and clear metabolic waste products out. And in this study, they looked at the ability of this to clear out beta amyloid. Beta amyloid is a protein which has a tendency to coagulate, forming plaques and tangles in the brain, and when that happens, you've got Alzheimer's disease. So this is one of the major culprits thought to be involved in the formation of Alzheimer, and the problem is that it collects in those interstitial spaces. So they looked at what happened to just the normal rate at which this gets cleared out of those spaces. across 4 hours of normal wakefulness and across 4 hours of sleep. And it might not look like this is falling that much faster, but when you actually calculate the rates, what you see is that when these are in rats, because they don't want to do this in humans, they're injecting radioactive isotopes. The rate at which it's cleared is about 2% per minute, but when you're asleep, it's closer to 5%. And although this just came out in Science a couple of months ago, and it needs a lot more work, but it might turn out that this is one of those factors that determines whether or not your amyloid concentrations in the brain build up to high enough levels to lead to Alzheimer's. Your brain doesn't just turn off when you go to sleep. I've been talking now mostly about, I'd call housekeeping functions, bodily functions. I want to turn now to talk more about brain functions. And when we sleep, we have this sense that the brain just turns off because we lie down, we close our eyes, if we're lucky, we fall asleep, open them later, and it's morning. It's like nothing happened in between. But all sorts of stuff is happening during the night. If you look at the actual depth of your sleep across the night, you've got this 90-minute REM cycle here. So REM is rapid eye movement sleep, REM sleep. In general, the names of our sleep stages are very boring. 1, 2, 3, 4. But REM we named after the band, so we think that's pretty cool. And REM actually stands for rapid eye movement sleep. And every 90 minutes, humans go into REM sleep. You'll notice that after an initial period of about 10 minutes of sleep onset with very light sleep, you descend into this non-REM sleep, deeper and deeper sleep. The deep sleep is called slow wave sleep. I'll show you why in a minute. But you have these couple of cycles with a lot of slow wave sleep, and then the slow wave sleep sort of peters out, and you start to see more and more REM sleep. So the slow wave sleep comes early, the REM sleep comes late, but this 90-minute periodicity goes all across the night. In a mouse, this whole thing is 5 minutes long, the REM cycle. So they're doing it much faster. And we've got no clue about why we have these differences in cycle length. Lots of, I left out my favorite. So there's this light stage 2. This is light non-REM sleep that's sort of distributed throughout the night. And each of these must have evolved for some reason, because they've been sustained, maintained across at least all of mammalian evolution. And we think that what's actually the reason for this is that each of these are providing a unique neurophysiological and neurochemical environment that's optimized to certain types of memory processing. So what do we see in terms of the differences in these stages? Well, we see differences in the electroencephalogram, the brain waves. Here's those large slow waves of slow wave sleep, stage 4 sleep. This is 2 seconds. The whole thing is about 15 seconds long. So look how different the brain activity measured way out on the scalp. I mean, we're literally taking a voltmeter, like you use in a car or something, and putting it here and here and measuring the voltage. And you're getting enough activity that's synchronous in the brain that you can hear it all the way out at the scalp when you see these large slow waves. REM sleep looks entirely different. This is the electrooculogram, eye movements. Here you can see those bursts of rapid eye movement, eye movements just jumping back and forth with rapid saccades. None of that in non-REM sleep. At sleep onset, you have these slow rolling eye movements, function unknown, mechanism unknown. It's a great field because we know almost nothing about what's going on here. Gives you lots of grant writing opportunities. And this is the electromyogram. This is a measure of muscle tone. As you might expect, as you go from full wakefulness into deep sleep, your muscles relax more and more. But then when you come back up to REM sleep and your brain gets all activated again, your muscles actually become paralyzed. There's a brainstem pathway that paralyzes your body. If anybody, I can't see, are there any people out there at all? These lights are really strange. It sounds like there's just a laugh track being played out there or something. But So I can see, how many have ever had an episode of sleep paralysis where they woke up? Raise your hands high, come on. So, I don't know, a quarter of you maybe, where you wake up and your body is paralyzed. That's because you've woken out of REM sleep to full consciousness, or almost full consciousness, but your body hasn't come out of that paralysis. And Rich McNally at Harvard actually has suggested that all of the alien abductions. Well, no, think about this seriously, because first of all, when this happens, so how many of you who raised your hand with sleep paralysis had hallucinations as part of that process? So some, but not so many. So it's not uncommon to hallucinate because you're, again, coming out of REM sleep, which is your dream stage. So here are people who report that they wake up, they are paralyzed. They always report that they're paralyzed. They see strange creatures, and then strange things happen. And the only thing that's different from normal sleep paralysis is they seem to then fall back asleep before they finally wake up. If you go back 150 years, it wasn't alien abductions, it was angels and devils who were coming into your room. So it might be that that's actually what those alien abductions are all about. So those are some of the features that change across the REM, non-REM cycle. But we also see changes in neuromodulation. So those hormones, those neurochemicals, those neurotransmitters that are used to modulate the activity of the brain overall, things like acetylcholine, norepinephrine, serotonin, they vary across the REM, non-REM cycle. And if you don't know those chemicals, those neurotransmitters, you might know the drugs that interact with them, scopolamine and atropine, affect acetylcholine. The monoamine oxidase inhibitors affect norepinephrine. The SSRIs, Prozac, all of those, and LSD act on serotonin receptors. So these neuromodulators change the overall behavior of the brain and the mind at the same time. And as you go across the sleep cycle, while in active wake, all of these will be being released at high rates. Then as you approach sleep, they quiet down. And when you go into that deep slow wave sleep, you get this bias towards just the norepinephrine and serotonin being released. And then in REM sleep, the whole thing flips on its head. So you're in a completely different brain state when you're in REM than when you're in non-REM sleep. We can look at regional brain activation. When you go into slow wave sleep, the whole brain quiets down. Glucose, oxygen utilization, they drop about 20%, pretty evenly across the brain. But then when you come into REM sleep, things get interesting. Some regions, some of you will love these names. The amygdala, who turns out to be a character in Batman comic books. The anterior cingulate, which has not made it into the comic books yet. These become more active. These are midline limbic structures. These are structures involved in emotional regulation. And there's others, medial orbital frontal cortex, another structure that mediates emotions. All of these are ramped up when you go into REM sleep, while other structures, most notably dorsolateral prefrontal cortex, become even less active. Well, dorsolateral prefrontal cortex is the part of our brain that is the center of logical reasoning, executive decisions, impulse control, logic, did I say that? So it's all of those higher functions. And so when we go into REM sleep, the emotional brain cranks up and the logical, rational, controlling brain shuts down. It's a real nice, fast description of what dreaming, which is most intense in REM sleep, is like. And that might be the reason that it is so. And the evolution says that it's going there for a reason, and we'll come back to that later. Just one last, I took out the one last example. Okay, so then one more function of sleep, and now we're starting to move into the brain functions and maybe the memory functions. By the way, I just noticed someone nodding off. This is the only talk, this might be the only talk you'll ever go to where the speaker will be honored. Right? So feel free to go to sleep. Because amongst other things, that sleep will help you balance your emotional system. And Matt Walker, who's out at Berkeley now, used to be with me at Harvard, did this wonderful series of experiments. He takes a group of subjects. Half of them he keeps awake all night, half of them he lets sleep normally. The next day, he puts them all on the MRI magnet and has them look at neutral, negative, and positive images and asks how are those different as a function of whether or not you were awake the night before. And he finds that the sleep-deprived subjects show a massive increase in the activation in the amygdala, which is sort of the center of fear response. In the sleep-deprived subjects, when they see those negative pictures compared to the healthy controls. So the amygdala is becoming more highly activated just from seeing those pictures. And it seems like the reason for that might be, remember I mentioned that medial orbital frontal cortex? You all wrote that down in your notes, I know that. So the medial orbital frontal cortex, which is located right here, right behind your eyes, is involved in the decision of whether something that is activating your amygdala is a real problem or not. So if you're at a movie and you're watching, help me, Friday the 13th, number 8 or something, your amygdala is screaming, run, run, run. And your medial orbital frontal cortex is looking at that image, those movies, in context and saying, it's just a movie, you don't have to worry about it, calm down. And it sets inhibitory signals back to the amygdala to quiet down the amygdala. And what you're seeing here is the strength of those functional connections between the amygdala and medial orbital frontal cortex are devastated in the sleep-deprived subjects. They're just not getting that feedback from the medial orbital frontal telling them that it's okay. If you've had partners, friends, anybody who's had a night of sleep deprivation, they're not nice people. They get angry easily, they get irrational, and some of it probably is because this regulatory system has broken down. So then he brings them back 42 hours later and he tests their memory. Okay? They get 2 nights of recovery sleep. Here are the well-slept controls. They have better memory for the positive and negative pictures than the neutral ones. We're all built that way. We remember the emotional better than the unemotional events in our lives. When you look at the sleep-deprived people, well, they only remember these about half as well. And they only remember these about half as well. But the negative ones, they've got them in spades. They get a 2-fold now enrichment of their recall and recognition of the negative events from 2 days back, 3 days back, than of the positive ones. It produces this entire shift in their perception of what's happened in their life. And in fact, I once made the claim that the entire Second Iraq War was because we had a bunch of decision makers who were sleep deprived. This is not meant as a joke. Who were chronically sleep deprived and making value judgments based on what they remembered about what they had been told. And what they were remembering is all the negative stuff and none of the positive stuff. You can't make good decisions if you're in that kind of a state. So sleep processes these memories, and it processes all of our memories from the day. And it processes different kinds of memories. It processes them in different ways. And so now I'm going to walk you through just some examples to give you a sense of the richness of what's happening while you sleep. Here's a simple little task. Type 41324 over and over on the keyboard. You can try it. It's sort of an ugly sequence that goes back and forth. If you have students do this, you let them do it for 30 seconds, rest 30 seconds, do another 30 seconds. They get about 14 sequences in the first trial, and over 12 minutes they get up to about 22 or so. We can train them in the morning or the evening, it doesn't make any difference. And then they kind of plateau out here. So we look at that level at post-training, and we send them away, we bring them back 12 hours later, and we give them just 2 trials now to see how much have they forgotten, or have they forgotten anything. So here's what we get. These are the 22, 23 sequences that they had at the end of training. These subjects trained in the evening are going to come back the next morning after a night of sleep. These subjects here were trained in the morning. They're going to come back in the evening after a day just being awake and going about their normal life. And here's what we get. Okay, after a night of sleep, you're 20% faster typing that. And in fact, your error rate is down. Now, these people haven't lost anything. We send them away for another 12 hours, give them another 2 trials. These don't show any change. It's across the day, but now these do manage to get the boost. So I will guarantee you that there's a whole slew of you out there in the audience who have played a musical instrument and had this following experience. You're practicing something, I don't know, a Chopin etude. There's a 4-measure section of that you practice and practice, and you can't get it. Every time you do it, your fingers crumple up, and you just slam the piano down. You think you should take up the violin or something. You go away. You come back the next day, you open the piano, you sit down, and you play it perfectly the first time through. And that's exactly because these sleep-dependent processes are taking the information that was initially learned and processing it further. If we have you do this task in the MRI magnet again, you're recruiting new regions of your brain to do the task after you've had a night of sleep. You're doing it differently. You're doing it in a more sophisticated way, and a way that you don't learn until you sleep, and you learn it while you sleep. But that's a kind of boring task. What does it take? It takes stage 2 non-REM sleep late in the night. Okay, if you look at how much they improve, 10, 20, 30, someone got up to 40%, it really seems to depend very heavily on how much of that light non-REM sleep they have late in the night. So it looks like motor skill learning is related to this particular sleep stage. Maybe that's why that sleep stage originally evolved. Now we can go to a different kind of task. Let's just talk about verbal memory. Okay? Here's a task where we have subjects listen to an audio tape with lists of words on it. And they're told, remember these words, we're going to test you on it later. So that's their instructions. To give you a sense of what that's like, I'm going to do it with you. So we need to bring the lights up now so we can see people out there. I'm going to show you a list of words. I want you to remember them because I'm going to test you on them. Ready? Here we go. Okay. So normally, if we were going to do a relatively fast retest, we might do 20 lists just to make it more difficult for you. In our study, we did 8 lists, but we were testing after 12 hours, mostly not just 20 minutes. Here you've got it dirt simple because it's just one list, and we're going to test you right now, okay? So I'm going to show you some words, and if you remember seeing it on the list, raise your hand. Now, for those of you who aren't physicians, it turns out that back here there's a muscle that's called an extensor muscle. And that's what gets your hand from here. Okay? Okay, I am so tired of people going. You want to show everybody around you how smart you are, right? Okay, so seriously raise your hand and hold it there. Not yet, you don't. Gee. Yes, you've seen the crosshair, right, okay. Okay, let's go. Word number 1. No, okay, how about, okay, good extensors, I like that. Okay, this one, okay, not so hard, right? Nobody, okay. My bad. Okay. So when we do this with a large number of lists, we'll get 80% of subjects false alarming on these words. Each of the lists is constructed by taking a word like doctor and taking it to a class of 200 freshman psych students in some college and say, write down the first 10 words that come to mind when you think of doctor. And then we cherry pick the high frequency ones. We put those in the list and we leave off the word doctor, okay? So you can think of this, and it has been described as a false memory task, because those of you who raised your hand had a false memory, right? You remembered seeing it, but you hadn't. We think of it more as a gist task, because what it's showing is that your brain is very, very facile at taking in information and extracting the gist. I mean, this is a list of words about doctors, right? And your brain figured that out. So the question is, what happens to those memories, both the memories for the words, that you did see, and for the words, these critical lures, the gist words, for your false memory for those words. So we take two groups of subjects, we train one in the morning and one in the evening and test them just 20 minutes later to find out, as I did here, how many of the words people could remember. This is not done with recognition, it's recall. We give them a blank piece of paper and just say, write down all the words you can remember. But it's essentially the same. And so we take those two groups in the morning and the evening, first of all, to make sure that there's no time of day effect. People aren't better in the morning or the evening, and they're not. They perform identically. And then we take that as a baseline and have two groups that come back after 12 hours, either training in the morning and testing in the evening, no sleep, training in the evening, testing the next morning, a night of sleep, and compare how they do to how the groups did after 20 minutes, okay? So what do we see? Let me walk you through. So for those who were awake from morning to evening, they forget about 40% of the words that they would have recalled after just 20 minutes based on those control groups. If you sleep during those 12 hours, you forget less. And it turns out that the reason you forget less is because you're not having tens of thousands of other words bombarding you during that 12-hour period like the wake group. We repeated the study in a nap protocol where people train at noon and then half of them take a nap and half don't take a nap, and then we test them out at 5 or 6 o'clock, so they've both had the same amount of time awake, but just that some of them have also gotten a nap, and then these two numbers look the same. So it just seems to be passive protection. But what's interesting is what happens to those memories of those gist words, the words that they didn't really see, but that hold the core of the information. And across wake, they're still forgetting 20 or 25% of them, but over a night of sleep, they actually get a little bit better. It's not statistically significant, but it's significantly better than everybody else, all these other conditions. So while you're sleeping, but not while you're awake, your brain will hold on to the gist of what you've learned and allow your mind, your brain, to forget the details. You don't always want to do that, but very often you do. And the brain does this not when you're awake, but while you're asleep. And there's no specific stage. It turns out the rule is not slow wave sleep. So when you look at how many of those words they can remember, both in the overnight study and the nap study, the more slow wave sleep you have, the more poorly you perform. And we think the reason for that is that slow wave sleep is actually very good for detail memory, and that's not the right way to do this task. You don't do well in this by remembering individual words. You do well by remembering the gist words and then going from those words. So if I asked you now to remember words from the list that I showed you, you'd start out saying, okay, they're all words about doctor, right? And that's what you see when they write them down. They write down a bunch of words about doctors, then a bunch of words about cups, and a bunch of words about windows, which are 3 of the lists. And so that technique of going for the detail, which is what slow wave sleep seems to be good for, doesn't work in this case. Oh, I love this one. So this is a wonderful study. In this study, your job is to learn to predict the weather based on these cards here, okay? On each of 200 training trials, you will see 1, 2, or 3 of these cards, and you have to predict whether it's going to be sunny or rainy. Okay? You're smart people. Come on. Not a problem. So maybe on the first trial, you see the diamonds, and it turns out to be sunny, regardless of what you guessed it was. If you're a Harvard student, as we did this with, you say, whatever. I mean, it's like, okay, I don't know what to do with that. Second trial comes along. Oh, it's the circles and the triangles, and it's rainy. Now, notice that you're all creating models in your minds already, right? That's what the human brain does in spades. It looks for patterns, and it learns patterns, and it dissects information to get patterns. So you're coming up with ideas like, well, okay, maybe this card predicts sun, and these two predict rain. Or some of you will say, well, maybe one card predicts sun, and two cards predict rain. I've got 198 more trials. I'm going to figure this out. Third trial comes along, and you say, okay, we're going fine. And it turns out to be rainy. And at that point, you fall apart. You literally give up trying. I mean, at first you say, oh, I must have remembered it wrong from last time. But then over and over this happens, that the same card patterns give you different results. And the reason is that each of these cards has a certain probability of predicting sun or rain. So 80% of the time this card appeared, it ended up being sunny, but only 20% of the time for this. It is a probabilistic task. And the human brain, although very good at intuiting these things, is really horrible at learning them in a declarative way, in a way that they can explicitly say, these are the rules. So after we do 200 training trials, we give them 100 test trials where they just see the patterns, but we don't tell them whether they got it right or not. So we can see how they're doing. And they're getting 75, 80, maybe even 90 out of the 100 right, which is way better than the 50 that would be chance. But nobody's at 100% of always guessing the most likely case. And that's because they don't really know the rules in that absolute way that they can speak them and follow them. But they have a sense of it, and they get pretty good at it. So then we take them, we send them away for 12 hours, across the day, across the night. We bring them back, we give them the exact same 100 trials again. So first of all, do they remember what they learned 12 hours ago? Well, let's look at the weight group. They do. They get 2 more right, because it's 2% out of 100 trials. They get 2 more correct on average at retest than at training, but that's not significant. There's a lot of variation. We can't be at all confident that that's really doing better. But look what happens after a night of sleep. Okay? They're 10% better at doing this task. That's amazing. What is the brain doing while they sleep that takes the information in whatever form they've stored it and processes it to a point that the organism, the human being, can predict what's the consequences of changes in its environment the next day better than they could the night before. This is a phenomenal achievement. And you just do it by sleeping. You don't think anything's happening, but your brain is figuring out from whatever form it was stored in. I don't think it's going through them again when you're asleep and playing, okay, at trial 47, it was this one, but then at trial. No, but there's some sort of representation of that information that it can sharpen up and perform better at the next day. And this one requires REM sleep. There's the correlation. So these different sleep stages seem to perform different functions. And REM might be more for that rule extraction, that creativity, whereas the slow wave sleep might be more about just being sure to remember the details that you need to remember. We can push this even further. This is an experiment. Those others were from our lab. This was done in Jan Born's lab in Germany. This is one of the few experiments in the field that I really pouted about not having thought of to do first, because it's a brilliant experiment. He brings subjects in, and he teaches them how to solve a class of math problems. In this math problems, you're shown 8 digits, like this, all 1s, 4s, and 9s in various orders. And you're told to process that list to get just a single-digit answer. And you can do it this way. Look, if the first two digits are the same, then you write that same digit down as an intermediate answer. So 1 and a 1 gives you a 1. Then you take that one and the next one. If they're the same, you write it down again. But they're not the same. So you write down the missing one. What does that mean? Well, we've only got 1s, 4s, and 9s. So what's missing here? Okay. So now you got a 9 and a 4, and you write down. Come on, this is church. You got to do the responsive reading. 1 and a 9, you get 4 and a 4 gives you rule number 1, right? 4 and a 9, 1 and a 4, 9. You get to the end, you get the final answer. The instructions are when you've got the final answer, just press the return key, because they're actually not writing them down, they're typing them in. And we'll tell you whether you got it right or wrong, okay? They do about 80, 90 of these during training. What they're not told is that there's an easier way to do it. These sequences have been constructed so that the last 3 digits you calculate in your solution path is a mirror image, a palindrome, of the 3 before them, 419, 914, which of course means that this one way back here is the same as this one over here, which means that that's the answer. If you figure out this shortcut, you just do the first 2 steps, you hit return, you get out of there 4 times faster. Not bad, okay? So they do a group of subjects. Only about 10% of them figure it out during training. They take those out back and shoot them. The rest of them they send home for 12 hours, again, across the day or across the night. Now they give them 200 test trials to see if they can figure it out. Okay, what do they find? Well, if they train them in the morning, bring them back that evening, about a quarter of them will figure it out. Usually when they figure it out, it's about halfway through, about 100 trials in. They'll suddenly figure it out. If they train them at night and keep them awake in the evening and keep them awake all night and test them in the morning, it looks the same. So there's nothing special about night versus day. But if they train them in the evening and let them sleep overnight, they're 2.5 times more likely to discover this insight. I mean, think of what this is worth to a corporation, right? If you could increase the insights, or a government, or a student, or a spouse. I mean, if they could become 2.5 times more effective at discovering things that they didn't even know were there to find. They weren't sent home after training saying, okay, suckers, see if you can figure out the shortcut. They just said, come back and we'll test you again. But the brain looks for it anyhow. Now, what's interesting is that those subjects who figured it out the next morning didn't actually get any faster at doing the rote method. Remember, it takes them about 100 trials before they find the shortcut. They checked the speed at which the subjects were performing it, and they were doing it the same as they were the evening before. But the 40% of subjects who don't figure out the shortcut, they get faster. Again, it's as if you can do this. Oh, why did it? Yes, sorry, I thought it popped up some other stuff. Your brain going to sleep says, so what should I do? Should I try to really remember really well what those rules were so I can do it faster tomorrow? Or should I maybe step back and say, is there something else going on here that would be worth looking at? So it seems like in each of these subjects, on average, they do one or the other, but not both. And it was exciting to find out that those who got faster had more slow-wave sleep. Again, as if that slow-wave sleep helps them nail down that algorithm, those 2 rules that they learned the evening before. Which means that these guys here, of course, had less slow-wave sleep. And so how much slow-wave sleep you get in the night might determine whether your brain processes information in more of a gist, big picture way, or in a detailed way. And it's agnostic as to which of those is better. If there was no shortcut, right? If there had been no shortcut, these people would have really blown it because they wouldn't have gotten better and they wouldn't have gotten anything else. So there's not a right and a wrong necessarily in this, but the brain makes choices. And we're not sure whether this is a personality difference. Maybe people who are more detail-oriented have more slow-wave sleep. We don't know if some people in their brains unconsciously got a hint that there was a shortcut, and that led their brain to change how much slow-wave sleep they got the next night, because the amount of REM and slow-wave sleep you get, we know, is affected by what you learned the day before. Or maybe these people just had someone, or these people here, someone slammed the door when they were going into REM sleep, so they woke up and they lost that REM period and just ended up getting more slow-wave sleep. So we haven't been able to tease those sorts of questions apart yet, but how you sleep determines what you take home from what you learned the day before. There are real-world implications of this. I'm sorry, I have been bad. A lot of my slides as I've gone through have had names here that I have not called out. These are colleagues, students who do these studies with me. No one in science does anything alone anymore. It's always a collaborative venture. So I should have given you this disclaimer before. Whenever I said I did something or I found something, I always mean we. Okay, that's just the way science works. In fact, whenever I say we did something, they did it, right? So Emily Hoagland, who was a Harvard undergrad doing an honors thesis project, did this study where she showed that it's not how much sleep you get, but how much the sleep varies from one night to another. And that's basically what this is a measure of. If you're a stats geek, this is the standard deviation of total sleep time for the second through fifth night prior to testing. So if you have a value of 0, it means that you got the exact same number of hours of sleep on all 4 of these nights. If you're out here around 2, it means maybe you got 8 hours one night, 6 hours another, 10 hours another. And you can see that the more variation you have in your night, the worse your performance gets. And we call this the real world because these are scores on organic chemistry tests for Harvard undergrads. Okay? This is a summer course. This is the average of 4 hour tests that they take, their percentile rank in class. So for every hour variation you have in how much sleep you get on a nightly basis, you drop 17 percentile. And it doesn't take much of a mathematician to know that 95 minus 17 is not a happy camper if it's your grade, right? It's dropping you from the 95th percentile to the 77th. So just 1 hour variation in the amount of sleep you get. What about dreaming? I love dreaming. How many people remember their dreams? How many are embarrassed to raise their hands but don't remember their dreams? Okay, good for you. I'm proud of you. Good news, nothing correlates with not remembering your dreams, except that they tend to be people who fall asleep quickly, sleep soundly through the whole night, don't you hate them? And wake up with an alarm clock. And the consequence of that is that there's no time at which they can remember dreams. When people say, I never remember my dreams, I say, drink 3 large glasses of water before you go to bed. It's not a joke. You're going to wake up 3 or 4 times. You tend to wake up right at the end of REM periods. That seems to be the most fragile moment. And you'll wake up and you'll remember your dreams. Drinking alcohol won't do it because alcohol is a REM suppressant. So don't do that before bed. Do it in the afternoon. So Aaron Walmsley, who was a postdoc of mine, who's down at Furman University in South Carolina now, wanted to look at the correlation of this sleep-dependent memory enhancement with dreaming. So this was just the New York Times. See, learning while you dream. Well, that's not exact. Yeah, okay. They take liberties. So here's the task. She developed this maze task. It's a 3-dimensional maze. You have to navigate through it. And your task as a subject is to learn the layout of the maze, to sort of get a picture of how the maze is laid out. She trains them at noon. She tests them at 5:30. Half the subjects get a nap in between, half the subjects don't, okay? And then she looks at how well they were doing at the end of training compared to how well they did at test. Well, in the weight group, it took them about a minute longer, about 60 seconds, to get through the maze at retest than they were doing at the end of training. So they seemed to lose a little bit of that knowledge that they had gained. But if they had a nap in between, they're about a minute faster. So this is, this for you should now be same old, same as all the other tasks. Sleep gives you a benefit. But then Erin did two things. First, she asked a second group of subjects at the very end of the study, when it was too late to mess anything else up, did you at any time between the end of training and the start of testing have any thoughts, images, or dreams about the task? And it turns out in both the weight group and the sleep group, about half the people say yes, half the people say no. In the weight group, well, it didn't matter whether they had maze-related thoughts or not. They got a little bit worse. In the sleep group, it looks like this. They only seemed to be getting better if they said they had thoughts, images, dreams about the task. And we want to say dreams because, these guys had thoughts and images. But Erin came back and did her third study where she actually now woke people up at 3 times during the nap, and asked them, just tell me whatever was going through your mind. And the subjects in the weight group who were just sitting quietly for the first 10 minutes here and then watching really boring videos for the next hour, she asked them at those same times, what was going through your mind just a moment ago? Okay? So in the weight group, again, does it make a difference? There's only a couple actually in this one, so the number's not really significantly different, whether they had thoughts about the maze when they were probed at those 3 times. In the sleep group, doesn't look much different if they don't report dreaming about the maze. But if they report they were dreaming about the maze, they get hugely better at retest. And now we're feeling really cocky because this is better than an fMRI study. fMRI study might show that the hippocampus is activated or the amygdala is activated. But we've got dream reports. We know what was going on in their brains as reported by their minds while they were dreaming, while they were sleeping, that correlated so well with how much they improved. So we'll start with the wake subjects. Okay, what do they report? I was thinking about the game that I used to play in high school, Counter-Strike, because of the same layout, and also I was just planning and trying to remember the maze and trying to figure out the route. I love using Harvard undergrads as subjects. They are so neurotically driven to succeed and do everything perfectly that this is what they do in their spare time, right? They think about the maze. Here's another one. I was thinking about what we have to do in the second maze test, wondered if it was going to be like the same. Okay, so these are the kinds of thoughts that seem like they would be useful. They might help performance at retest, and yet they don't. Well, you can imagine what we must have seen in the dream reports. I was thinking about the maze and kind of having people at checkpoints. Well, there are no checkpoints, and there are no people. And that led me to think about when I went on this trip a few years ago and we went to see these bat caves, and they're kind of like maze-like. Thanks for sharing. This is not going to help them. How about I was looking for something in a maze? How about I was just hearing the music. There's some music that plays in the background for the whole task. Just hearing the music. These are profoundly useless dreams, right? But look, that's those people here. So what's going on? Well, what we think is going on is that the whole brain is working on a problem at the same time. And it's sort of like if you're in a corporation or in a university or any organization where you have some people who do one thing and some people who do another. It might be that down in the hippocampus, where we know the brain stores maps of spatial layouts, that in fact it's replaying and stabilizing and enhancing the memory of the layout of that maze. But we know from other studies that that information in the hippocampus doesn't get into our dreams. We've done the studies. We don't see hippocampal memories in our dreams. So that's not what we dream about. What else do we know? Well, we know, for example, that in the neocortex, in the bumpy front part of the brains, I showed you data for rule and gist extraction, right? That was the weather prediction task, the word lists. But actually the brain will also, if you show pictures that are mixtures of emotional and neutral parts in a single picture, it'll remember the emotional objects and forget the neutral parts while you sleep. So it does salience selection. And it can integrate new information into older networks of information. So all of these things we know from our memory studies are going on in the frontal part of the brain. And then we dream. And when we dream, what do? We do narrative development. Dreams are always stories. Dreams are almost never a picture or a slideshow or a PowerPoint presentation. They're stories. They've got a beginning, a middle, and an end, kind of, sort of. They certainly have a middle, okay? We do narrative development. We do a lot of theory of mind in our dreams, right? We spend a lot of time in dreams trying to figure out what other characters meant by what they said or what they did or what are they going to do. And we do a lot of what turns out to be future projection. It seems like we take the events of our days and take elements of it and project it into a novel, imagined scenario. And so what we think is happening is that what we're seeing in the dreams is the brain sort of thinking, well, how might this information be useful? Could I use this information if I ever go down in caves again? Would that be useful to remember what I learned here? When I get retested in a couple of hours, was there anything I learned when I was in the caves that might help me perform better on that task? And what about finding things in mazes generally, or finding things in life generally? So the brain is sort of doing a random walk through association cortex, looking for ways that it might be able to use that new information. So I'll do a digression. After September 11th, 2001, we all walked around saying, I don't understand what happened. But come on, we did. A large plane, a lot of aviation fluid, high speed, tall building, wham. I mean, what's to understand? Well, what's to understand for me is I work in a 13-story hospital. Should I go to work tomorrow? I've got plane tickets to Amsterdam in 2 weeks. Should I cancel my trip? I'm going down into the subway. The guy in front of me kind of looks Arab, and I don't even know what that means, but that's my thought. And he's got a big backpack. Should I turn and run? It's not that we don't understand the event that happened as it happened, is we don't know its implications. We don't know going forward in our life how to use that information. In the case like something like this, it doesn't matter very much. September 11, it did. And so as we went to bed at night, and as our brain rifled through the events of our day, as it does, to try to decide what's important and needs to be processed, everybody on September 11th didn't want to close their eyes because they knew they were going to see the buildings exploding, the people jumping out, the buildings collapsing. And in fact, the filling of prescriptions for sleep medications nationwide went up 20% in the 2 months after September 11th because that pre-sleep processing became so painful that people couldn't sleep. So that is what we think the brain is doing. On the one hand, maybe down in the hippocampus, it's taking what it just learned and it's nailing it down. It's going to be better on that maze the next time. But it's also asking the question, so what? Who cares? What does it mean for me? So sleep is not about curing sleepiness. What a fun idea. It's critical for the maintenance of immune function, hormonal function, psychiatric health, metabolic clearance, metabolite clearance from the brain, emotional balance. And each stage of sleep plays an important role in the offline evolution of recently formed memories. And I like the word evolution instead of consolidation because our memories change throughout our lives. All you have to do is look at your spouse or remember your parents, how they used to sit and natter at each other. No, honey, that didn't happen at the Schwartz's house. That happened when we were at this party at the Callahan's house. And you're sitting there saying, why do they care? But our memories change. Our memories change as our lives progress. We remember clearly the important parts. The other parts become less clear. Every time it turns out we remember something, our brain modifies it a bit. So our memories evolve over time, and sleep plays a big role in it. Sleep can strengthen motor memories, extract gist, discover rules, draw insights from these memories. You saw examples of all of those. Other studies have shown that sleep can stabilize, selectively maintain parts of memories, and integrate new memories with old ones. And our dreams reflect these complex processes of memory evolution. But most importantly, these systems of memory evolution carry out what may be the most sophisticated function that the human brain performs. It's building a model of ourselves and of our world so that we can understand better how to move through that world in the future. And as it builds these associations, it really creates the meaning in our life, because the meaning of things is how we put them together. And that seems to be something we do in our sleep, and something that all of you should do tonight. Thank you. So now it's beat up the lecturer time. That we have two people going,
We have the
1
first
hour
question.
and 1 minute.
I know.
Yes.
Yes. We have the first
I'm so
question
proud.
right here.
There are two people with mics going around to people who have questions. So who's first?
This lady right here.
Yes.
Hi, thank you very much. That was very, very interesting. I have some ideas in my head about the quality of sleep that we get during the night and the quality of sleep that we get during the day.
Mm-hmm.
And assuming that somebody works during the night and they make up the sleep they lost during the day, is this sleep equivalent? Is the sleep that you do at night equivalent to the sleep that you do during the day?
That's a great question. When I was young, to avoid my parents when I was a late adolescent, I used to work in a lab, and I would work at night instead of during the day, so I just didn't have to be home with my parents in the evening. And I remember very clearly my father telling me that that wasn't okay, because he says, you can't get a good night's sleep during the day. I said, okay, that's a good idea. So it turns out you can't. That sleep during the day outside of your normal circadian rhythm just is not as good. You don't sleep as deeply, you don't fall asleep as easily, you don't stay asleep as well. And the quality of it is lower. That's not talking about naps. Naps are actually super cool, because for all of these paradigms where I show you overnight improvement, a 90-minute nap will give you as much improvement as a whole night of sleep, which is really cool. And it's kind of weird, because sometimes a 5 or 6 hour night won't give it to you. So there's something about the nap as a nap that is highly efficient. But when you try to get all of your sleep, when you try to sleep for 8 hours during the day, you get much less total sleep time, and the quality of it is reduced. We haven't done these kinds of studies, but there are studies with pilots and flight attendants who do transcontinental flights between the US and Europe, and their cancer rates are higher. And we think it's immune function problems because they're not sleeping the way they should.
Next question here.
Hi. I kind of have two, but one's really quick, I promise.
Okay.
Going back to that study from the Harvard undergrads who were taking the chemistry test, and it was the differences in the amount of sleep each night. I'm wondering about the correlation there. Were they given certain amounts of time to sleep, or were they just asked later how much they slept? For instance, is someone who sleeps 6 hours one night and 10 hours the next, maybe they're just a more irresponsible person, and maybe that's why they
Yes,
perform
yes.
worse?
So this is, in fact, totally self-modulated sleep with no one telling them how much. So exactly that sort of thing might be the case. You'll notice we did 2 to 5 nights before. We didn't want to count the night before because you can imagine that some students only get an hour or 2 of sleep the night before because they're cramming for the exam because they're in trouble already. So we didn't include that night. There's no systemic variation across the other nights. But it could be personality. We don't know why they're varying it, and we don't know the causal link. Chuck Seisler's group is now actually going to do some studies with students where they pay them to sleep more. You can't really do the study where you ask them to do something that you think is going to, flunk them out of college or something. But you can ask them to sleep more and see if that intervention makes a difference.
Thanks. And my other question is just, if I sleep really deeply, but have a lot of vivid dreams that so I wake up the next morning tired, like feeling like I haven't slept that much because I feel like I was running around all night, even though I was actually asleep the whole night, what stage am I getting stuck in?
Well, if you're having a lot of vivid dreaming, that's most commonly in REM. If you're remembering a lot of dreams, then you're probably waking up a lot during the night. And so it might be, for example, a situation like sleep apnea, where these people who, in the lab, we see they're waking up 60 times an hour. You ask them the next morning, so how many times did you wake up last night? And they say 3. Because if you wake up and fall right back asleep, you have no memory of it. So your sleep may not actually be as good as it is. Can't say more without bringing you into the lab.
Okay, here we go, right here.
Yes.
Thank you. I've heard the argument that different kinds of meditation may have similar effects to sleep, and I was wondering if you've looked at that and if there are different kinds of meditation that mimic different kinds of sleep, or if they're entirely different.
I love the question, and I hate you for asking it, because we've tried to do the study twice, and for completely logistical reasons of not having enough staff and organization, we haven't been able to complete either of them. It's a very, very good question, and it's an important one. I know Richie Davidson works a lot, he's at Wisconsin and works a lot with the Dalai Lama and a lot of the really intense meditators over in Asia, and he's asked them questions about how much they sleep, and they say they sleep much, much less than people normally do. And he says, and then I asked them, well, do you ever fall asleep when you're meditating? And he says, they all laugh and say, oh yes, all the time. So we don't have those numbers in a useful way yet. But it's a very good question. It's related to the question that if we stayed around long enough, someone would ask, which would be about lucid dreaming. Lucid dreaming is when you're aware of the fact that you're dreaming and sometimes can start to actually control dream content, and can you then improve your memory on a particular topic by leading yourself to dream about it. And that's another study that no one has done yet. But there's all these subtle differences, the variations that we just haven't looked at. Until 2005, I think it's safe to say there were only 3 labs in the world, one in Germany, one in Canada, and my own, that were focused on sleep and memory. And it's growing exponentially now, but it's still a really small cadre. And huge numbers of the exciting questions haven't been asked. So here's a plug. If any of you work in a lab, and you work with some clinical population, for example, and you want to know if bipolar patients, because that's who you work with, whether they have normal sleep-dependent memory processing, drop me an email. All of these tests are available for free, and you can go and study them yourself. You just have to make me senior author. No, that's not true. A little acknowledgement at the bottom of the last page.
Next question here.
I have a question with 3 parts. And basically what I'm trying to get at, I think probably a lot of other people are, is sort of what is the optimal amount of sleep? I'm somebody that most of my work is mental. That is, I'm an engineer. I do advanced development work. And on the other hand, if you sleep too much, it's taking away time. So the first question is, what is the optimal amount of sleep to get? And also, does this vary a lot with different people? Because you hear, and in fact, the advertisement for this program mentioned, these entrepreneurs that said they were very successful
I
because
hate
they only
that.
slept on with 4 hours of sleep. And then third question applies specifically to myself.
Do them one at a time. I got a very
Okay.
small memory.
Sure.
So, yeah, well, I could answer them all three tomorrow morning, but
So the
so the
first,
first one was optimal.
yeah,
total
so the
sleep time.
optimal amount of sleep to get
Right.
for
So
mental, good
we,
mental
you
performance.
changed it there. So he said for mental performance, because remember, I got a list up there of 6 functions for sleep, and there's no reason to assume that they all require the same amount. This is sort of the question, how much vitamin do I need? How many milligrams of vitamin do I need each day? Well, you need different amounts of different vitamins, and it depends on your metabolism and how you're using it. So we don't have a good measure for how much sleep you need. What we classically would say, what I'll say is, if you drink caffeine, if you ingest caffeine before 10 a.m.
I do not.
Okay, but if you do, you're self-medicating because you're not getting enough sleep. If you sleep longer on the weekends than you do during the week, you probably are not getting enough sleep during the week. If you think it's a joke to try not using an alarm clock, then you're definitely not getting enough sleep. Because in general, we think that your body will get the amount that it needs. I'm not convinced that you can get too much sleep. Despite what I thought when my daughter was younger, and I think that you get the amount of sleep. And there have been studies at the NIH where they had people spend 16 hours a day in the dark in bed. And at first, they did it for 3 weeks. At first, they would sleep 12, 14 hours. But by the second to third weeks, everybody's down to around 8 hours and 15 minutes. They would much rather be sleeping. I mean, they're just lying there in pitch darkness, but they can't. So I think the amount of sleep your body takes is the amount that you need. And about shortchanging your wake time, I think that's a bogus argument. I get into this argument with my students who are doing 4 hours of sleep a night. And I say, look, if you go from 4 to 6 hours of sleep, you're getting 50% more sleep time, right? And your wake time is dropping from 20 hours to 18. You're getting 10% less wake time. If you can honestly say to me with a straight face that you're not 10% more efficient on 6 hours of sleep than 4, I've got nothing to say to you. But you know you are. And I don't think there's any point at which you don't get more efficiency from the extra sleep to make up for the time that you lose. And what I've said elsewhere is, you don't have to make a life change. Try it for 2 weeks. Try going to bed an hour earlier and sleeping as long as you want for 2 weeks and see what it's like. You can always go back. Differences between people, they do sleep very different amounts. We don't know why. A lot of short sleepers are not as short as they say, so they got Thomas Edison there at 4 hours a night. But he was a notorious napper. He probably napped 2 hours a day. In fact, I don't know if you noticed in the Mays study, of the 3 awakenings, 2 were done just at the start, because you often get incorporation of waking events into your little dreams right at the start of sleep, in what's called hypnagogic dreams. And Edison, when he had a problem he couldn't solve, would sit in an armchair. I got to see the chair, it was much fun. And he would rest his arm on the arm of it, and he would hold a spoon between 2 fingers over a metal plate. And he would close his eyes and he would think about, how am I ever going to get that thing to work? And he would drift off to sleep. And I mean, this is the inventor genius. When he falls asleep, the muscle tone drops, the spoon falls, hits the plate, wakes him up, and he writes down religiously what was going through his mind, no matter how crazy it was. So he might have needed to get 4 hours of sleep a night so he could get all of that time to nap, to use that time successfully. And I actually believe that. I don't believe it when I say that Newton, that apple, it woke him up. That's why he got his theory. So we don't know why there's variation in sleep that way. A lot of people who say, I know someone who wanted to study people who said they got 4 hours of sleep a night. And of people who answered an ad saying they got 4 hours of sleep a night, less than 10%, when pushed, actually only got that little. They didn't count weekends. They did it most nights. They napped. Very, very few people. Lots of people only sleep 6. A lot of that is drug mediated. I mean, I go crazy. People say, Bob, I used to need 8 hours of sleep a night. But Starbucks came out with the Grande, right? And now I only need 6. I mean, think about that. That's implying that whole list of things that happen when you sleep, it doesn't happen. That all that sleep is about is curing sleepiness. And it's a cultural dilemma that we have. It's sort of like the drunk driving world that we have, where everybody, or the cell phones, right? You all know that nobody is safe driving and talking on their cell phone except you, right? And it's the same way with inadequate sleep. Bill Gates once famously said that his programmers were so dedicated that if they had a major deadline coming up, they would program 72 hours straight without sleep. And I said, Bill, it's Windows that they produced, right? Your third question now.
Yeah. Well, my just a question on what you said.
You only
there.
get one more. No.
Okay. Well, if I allow myself just to sleep as long as I want, the amount of time I'll sleep varies widely. Sometimes it'll be only maybe 4 or 5 hours a night. Sometimes it'll be like, 7.5 to 8. So should I be sort of evening it out and sleeping the same amount all the time?
It's good to even it out because you know how those REM cycles came and you got most of the REM sleep at the end of the night? If your brain doesn't know how long you're going to sleep, it doesn't know where to put that REM. So if it's expecting 8 hours and you only get 4, you're going to miss most of that REM sleep. So that's why we think that's the source of that problem when your sleep is varying a lot.
Okay, next question right here.
I have a general question. Pardon? Oh, okay. I have a question about lucid dreaming and how it comes up. I've been in the University of Washington sleep lab because I was tested for sleep apnea, but I also lucid dream. And I can write up to 5 sentences and 3 lines of code in my sleep, wake up, and do that immediately. I can also choose to either have a narrative dream, just go into regular REM, or what I deem to be REM, or just fall into the oblivion. So I'm curious, because it was not captured when I was in the sleep lab, I think I was anxious, so I did not lucid dream. Is there any speculation that that's REM? And how do lucid dreamers have good sleep hygiene? Do they lucid dream or not? Because I have the choice in utility.
So you see there's a whole bunch of questions. So lucid dreaming happens almost exclusively so lucid dreaming, again, is when you have that sudden realization, oh, this is a dream. And that happens ridiculously infrequently, right? You have all these dreams that are patently impossible, and it never dawns on you that they couldn't happen. Sometimes you become aware of that, and you become lucid. And if you do that a lot, you can start to find ways to manipulate the content of the dream. In studies that have been done in the last few years, it turns out that dorsolateral prefrontal cortex that I said shuts way down during REM sleep, in lucid dreamers, it comes back up online. So you sort of regain that control. And if you're like most lucid dreamers, you sort of live on a knife edge between losing the lucidity and just sinking back into regular dreaming, or waking yourself up. So it's sort of an in-between state. And I don't think personally that there's any problem with doing as much lucid dreaming as you can. Yeah, but I think it's fine to do it every night because in reality, I talk about dreaming as being a REM phenomenon, but you dream most of the time you're in non-REM sleep as well. It tends not to be as visual, not to be as bizarre, not to be as emotional, but it's good, solid dreaming. And so probably out of an 8-hour night, we dream for 6 hours. So when you say you're lucid every night, that's for 5 or 10 or 15 minutes of the night. So it really doesn't interfere with the rest of it. Yeah, you just can't get that. You can't maintain it that long. Yeah.
Next question here.
Excuse me.
I was wondering if it is possible, or you think it may be possible in the future to either induce different phases of sleep or to control them or make them longer.
Yeah. The answer is yes, and I don't know that it's a good idea because people are going to start thinking they know which phase they want. It turns out that your brain does adjust on a night-by-night basis the relative amounts of time you spend in different sleep stages depending on your experiences during that day. So if I train you on a task that requires slow-wave sleep to get enhancement the next day, you will get more slow-wave sleep. If I train you on a task that requires REM sleep, you'll get more REM sleep. Having said that, there are studies being done now, some of them published, where they put two little electrodes on your head hooked up to a 9-volt battery and just put little current pulses into your scalp and then into your brain. And if they pulse it at the same frequency as the slow waves, they can increase the size of your slow waves and increase the amount of time you spend in that slow wave sleep. And they're just now coming out some studies that you can do it with sound pulses too. You can just have sounds pulsing at about 1 to 3 per second, burp, 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 at a volume that doesn't wake you up, but that will actually increase those slow waves. No methods offhand that people have come up with to increase REM sleep, but that's the partial answer of where we've gotten so far. Again, I don't know that I would recommend to anyone that there was a direction to go. The only place that it seems interesting might be with aging, because as you age, you lose slow wave sleep. You start losing your slow wave sleep at about 35, and it gets worse. Yeah, sorry about that. And I sometimes say you start to lose slow wave sleep that first time you can't remember a name, because there's an issue. Matt Walker, again, out of Berkeley, has data that says that the reduction in slow wave sleep is a better predictor of slow memory deterioration than age per se. So there's a question of whether in an aging population, trying now to restore slow wave sleep would be of value.
And a question here.
Hi, I wanted to say thank you very much. This was wonderful information. I think I've always been fascinated with sleep. I have a question pertaining to dreams. When you were talking about dreams, and I thought about what about deja vu? You know, over a long period of time, I realized that when I experience deja vu, it's actually because I had a dream about it either many months ago or many years ago. And because I tend to remember my dreams. And sometimes what I'll do is when I wake up, I write it down, because literally 5 minutes later, I could forget the dream.
Yeah.
Yeah, so the question is about deja vu, and if anybody does any research about that, or if you have any information on that.
There are people who study deja vu. I don't know that anyone has ever proposed. It's a fascinating idea that what you're remembering are dreams. I would, if you asked me to guess at it, I would guess not, because deja vu is almost always of reasonable, believable events, and our dreams mostly aren't. But some of them are, and maybe those are the ones that, when they linger, become deja vu. I'll tell you something. We just got a paper out a few months ago. We sort of stumbled in with Tom Scammell. Tom Scammell is a narcolepsy clinician and researcher at Beth Israel, where I work. And he commented that, he said, these people with narcolepsy, they wake up in the morning and they think their dreams really happened. And I said, well, that's weird, because I'm like that. So we actually did a study, and 80% of patients who have narcolepsy, and to be technical, narcolepsy with cataplexy, so the full-blown narcolepsy, they report that sort of on a weekly basis, they have to actually do fact-checking to figure out whether something they think happened actually did happen, or whether they dreamt it. So that might be related to that, to your sense of deja vu, again, that something happened that you then realize was a dream. But I've never heard that, and I think it's a fascinating idea.
This will be the last question right here.
Hi. Do people who suffer from chronic fatigue syndrome tend to have similar sleep patterns as those without, or maybe do they not?
No, they don't. They don't. In fact, they have alpha wave intrusion into their slow wave sleep. That's what you see in the EEG. They have disturbed sleep, and sleep is very clearly a major contributor to at least the extent of the fibromyalgia. Harvey Moldovsky in Toronto took college students and started to disrupt their slow wave sleep in ways similar to what he saw with fibromyalgia patients. And he stopped after several days because they started reporting pain. And he started to worry that he might be inducing a condition. My wife actually has fibromyalgia, and we track it, and if she has 2 bad nights of sleep, her pain gets worse inevitably and remains bad until she manages to get a night that she can get the extra sleep back. So not only is the correlation there, but we're pretty sure that the causation is there, or at least as a contributor. I would say for all of these psychiatric conditions, I'm not saying that it's inadequate sleep or poor sleep that causes depression, but that it exacerbates it. Patients with bipolar disease, if you sleep deprive them, it flips them over into the manic state. So it can trigger the mania if you have inadequate sleep. And PTSD, it's an entirely different hour lecture. PTSD may actually be a sleep disorder. It might be due to a failure of that kind of integrative gist extraction that happens during sleep, because patients with PTSD have a traumatic memory that doesn't get resolved, which means that they don't integrate it into the rest of their lives. They don't know how to move forward in their lives. It's like I was saying after 9/11. Most of us had that sort of paralysis in the days immediately after, but over a week or a month or 2 months, we sort of got our life back on track. I mean, it was forever changed, but we knew how to go on with our lives. And what happens with these patients with PTSD is they never manage to do that integration. And from our studies, it looks like that's an integration that usually happens during sleep. So it could literally be caused by a breakdown of those processes. So fibromyalgia, whether it's caused by that or just exacerbated by, we don't know. But it's part of the wonderful world of sleep. It's part of all the things that we still have to learn. More than most fields in medical science, it's growing in these huge conceptual leaps of bounds. And sometimes I feel that all I'm really learning is what my mother told me, which really sort of annoys me. But if you go back and sort of go a little bit hyperbolic, if you don't get enough sleep, you're going to end up sick, fat, and stupid. So get some sleep tonight. Thank you.